It's the most universal headache in software engineering. I think we've all been there.
Oh, absolutely.
You've just wrapped up a new feature, everything works perfectly on your laptop, the database connects, all the tests are green. You
Flawless.
hand it off, it moves to staging, or even worse, it goes straight to production and boom!
Nothing. It just breaks.
It's the classic, well, it works on my machine. And that one phrase has probably killed more productivity and reliability than any other.
I think that phrase should be permanently retired.
Mm-hmm.
And, that inconsistency, that drift between all the environments, that was the single biggest hurdle to building scalable systems for years.
It just introduces so much risk.
A huge amount of drag and risk. And so our mission for this deep dive is to really get into the technology that, for the most part, solved that problem. We're talking about Docker.
And we're not just going to cover the 101 basics. We're going to go from the absolute foundation, the blueprint, the Docker image, all the way up to the massive skyscraper architecture. We want to show you exactly how these simple, fundamental building blocks can underpin these huge, resilient, high-volume production systems that we see today.
It's an architectural journey. We'll start with images and containers, then see how they're used to build, say, dynamic microservices, and then we'll get into the really critical infrastructure patterns.
Like monitoring, traffic management.
All of it. And fault tolerance.
Yeah.
How do these systems absorb failure without just collapsing? This isn't a tutorial. It's a look at the whole architectural picture.
Okay, so let's start at the absolute beginning, the foundation. You mentioned the blueprint. If we're trying to solve this environmental drift problem, we need consistency above all else.
Precisely. And that is the Docker image. So for a moment, just forget about the running application. The image is a read-only immutable template.
Okay.
It's a complete static snapshot of your application and everything it needs to run.
And by everything, you mean literally everything. The code, the libraries.
Everything. The code, the specific runtime version, whether that's Python 3.10 or Java 17, all the system tools, all the libraries, all the config settings, it's all baked in.
I think the key insight there from a system design perspective is the word immutable. If the image is the blueprint, you can't change it after it's built, can you?
You cannot. And that is the genius of it. Because if an issue pops up in production, you know for a fact that the image running there is the exact same set of bits that you tested in staging.
There's no drift.
No drift. This reproducibility is guaranteed because images are built using a Dockerfile, which is really just a text file with a list of automated instructions.
Yeah.
That automation is what guarantees the consistency.
So we have this perfect, tested, immutable blueprint, the image. What happens when we actually want to run it? That's where the container comes in.
Right. The container is the running instance of that image. It's the lightweight, standalone, executable environment.
So if the image is the class, the container is the object.
That's the perfect analogy. It's the instance of that class.
Yeah.
But the real magic of the container is the isolation.
Okay, how does that isolation work on a fundamental level? What's actually stopping one app and one container from, messing with another one?
It's really clever.
Hmm.
It leverages core features of the Linux kernel, specifically things called namespaces and control groups, or C groups.
Okay.
Namespaces provide the isolation. They trick the application inside the container into thinking it has its own private file system, its own network, its own processes.
So it's in its own little world.
Completely. And then C groups handle the resource limits. They make sure one rogue container doesn't suddenly eat up all the CPU or memory on the host machine.
Ah, so you can think of them like isolated apartments in a building. They don't know their neighbors exist, and they can't steal their electricity.
That's a great way to put it. They're secure, isolated, and resource constrained.
And this distinction between the image and the container, why is that so critical when you start thinking about scaling a really high traffic application?
Because it completely separates the concerns of construction from the concerns of operation. You spend all your time perfecting this one single image, your one reliable blueprint.
Right.
Then, when traffic spikes, you don't rebuild anything. You just tell the system, hey, spin up 20 more instances or 50 more, 50 new containers, all running from that one single verified source.
So consistency at scale comes directly from that immutability in the image.
That's it.
Okay, let's move up a level from the building blocks and talk architecture. We've got a system now where every service authentication, user profiles, whatever, is living in its own isolated container. In a microservices world, they have to talk to each other. How do we stop them from becoming so tightly coupled that we just end up with a distributed monolith?
That is the classic challenge. And the answer is decoupling. The key technology for that is almost always a message queue.
Right.
So we orchestrate systems like RabbitMQ or maybe Apache Kafka, often running in their own dedicated containers, and they handle all the communication.
So instead of service A making a direct blocking API call to service B, which could fail,
Right.
it just drops a message into a queue and moves on with its life.
Exactly. You get asynchronous communication. If service B is busy with a heavy job, service A doesn't have to sit there and wait. The request is just queued up.
And that must do wonders for system resilience if service B crashes.
Service A doesn't even notice. The queue just holds the messages until service B comes back online or a new instance is spun up. The system as a whole doesn't fail.
That makes a ton of sense for resilience, but doesn't that just add another complex moving part, another point of failure?
Yeah.
How do you choose the right tool for that job? Say, Kafka versus RabbitMQ.
That is a critical architectural trade-off you have to make. If your system just needs fast, transient, delivery-like distributing tasks or sending quick notifications, a lighter in-memory queue like RabbitMQ might be perfect. But if you need persistent guaranteed message delivery, or if you want to do event sourcing or be able to replay old data streams, what we call durability, then you need a much more robust log-based system like Kafka.
And the container just provides the stable runtime for whichever one you choose.
Yeah, the choice is about the job, not the environment.
So let's pivot from the data flow to raw performance. Decoupled services can get pretty chatty, and hitting the main database for every single little request is a great way to kill responsiveness.
Oh, it's a performance killer.
So where does high-speed caching fit into this containerized world?
Caching becomes absolutely non-negotiable. We deploy high-speed data stores, usually Redis or memcached, also in their own Docker containers, and they act as this dedicated layer between our application services and the primary database. It's your high-speed data access layer.
And if we look at the trade-off there, Redis versus memcached, what's the typical thought process for an engineer designing this?
You're usually weighing complexity against raw functionality. Memcached is hyper simple. It's just extremely fast key value storage, and that's it. Very focused.
Very focused. Redis, on the other hand, gives you more complex data structures, lists, sets, even geospatial indexes, and importantly, it has options for persistence.
So the choice really comes down to what features your application actually needs.
Exactly. Since they both run perfectly inside containers, it's not an operational decision, it's an application-level one. But they both serve that core purpose, intercepting common requests to slash your latency.
So now we have these individual containers talking asynchronously. They're boosted by high-speed caching. But for any real production system, you have to know what's going on inside. You need to manage the traffic. We have to talk about the hard infrastructure layers.
Yeah.
The gatekeepers.
Absolutely. Now we're shifting focus to traffic management and observability. For all the incoming traffic and for the communication between services, we look to something like Envoy Proxy.
Okay, Envoy.
Think of Envoy as the intelligent, programmable gatekeeper for your entire fleet of applications. It routes traffic, it handles really sophisticated load balancing, and it's critical for enforcing security and retry policies. And architecturally, the most common way to deploy this is the sidecar proxy pattern, right? Can you break down why that's such a powerful design choice?
It's the ultimate form of decoupling. So the sidecar, the Envoy proxy, runs in a separate container but in the same logical group as your application container.
So they're paired up.
They're paired up. It intercepts all incoming and outgoing traffic, but, this is the key,
Yeah.
your application code doesn't know it's there. The app doesn't have to know anything about routing rules or encryption or observability.
Ah, clean separation of concern.
Perfect separation.
Yep.
The application engineer focuses purely on business logic, and the platform or DevOps team focuses on the proxy configuration.
And that proxy gives us an incredible amount of visibility into what's happening. So what does that mean for the eyes on the system? Envoy is just constantly emitting this rich data on every request.
Right. And that leads us directly to the metrics mindset, which is powered by Prometheus. Prometheus is a monitoring system designed specifically to scrape and collect all these metrics, not just from Envoy, but from every single containerized application. We're shifting from looking at logs, which tell you what happened in the past,
To looking at metrics, which tell you how the system is behaving right now.
exactly, in real time.
And the value here isn't just making a pretty dashboard to look at, it's about proactive intervention.
It's totally proactive.
Yeah.
By analyzing these metrics, traffic flow, latency percentiles, error rates, you get this real-time insight into the system's health. And crucially, Prometheus lets you define alerts on specific thresholds.
So if latency on my checkout service goes above 500 milliseconds for 5 minutes.
An alert fires. And you're fixing the problem, often before a single customer even reports that the site feels slow.
Okay, so if we connect that metrics mindset back to resilience, let's talk about the inevitable failure. A service gets overloaded, it starts throwing errors. What happens?
If you don't handle that correctly, you get a cascading failure. That is the architect's worst nightmare.
The domino effect.
Exactly. Imagine Service A calls Service B, which is now slow. So Service A starts backing up its own request pool, waiting for B. Pretty soon, Service A becomes slow, which then drags down Service C, which depends on A, and the whole system comes down.
So what's the solution?
The solution is a pattern called the circuit breaker.
It sounds like something from an electrical panel.
It is. It's the exact same concept.
Yeah.
It acts as a safety switch. The circuit breaker is just a little piece of logic that observes the calls to a dependency. If that dependency fails too many times, or if it times out too often,
The switch flips.
the circuit automatically opens. It stops all traffic from going to that unhealthy service.
So it isolates the failure.
Precisely. It prevents Service A from wasting its own resources trying to call a failing Service B. Instead, Service A can immediately fail the request with a known error, or maybe fall back to a cached response. It gives the unhealthy service time to recover without being hammered by more requests.
And that protects the integrity of the whole system.
It's what stops a small fire from becoming a 5-alarm blaze. And you implement this with libraries like Hystrix or Resilience4j right inside your microservices code.
So when you combine Envoy for traffic management, Prometheus for metrics, and circuit breakers for fault tolerance, that really is the trifecta for a resilient system.
It is.
Okay, we've built this resilient structure. Now let's talk about volume. Traffic always goes up. We need to scale.
The main way we scale in the container world is horizontal scaling.
Meaning?
It just means adding more container instances, more workers. You have your one microservice and you put a load balancer in front of it, and you just add more identical copies behind it to distribute the load.
And because our image is immutable, we can spin up 20 more instances and know they'll all be exactly the same.
Quickly and consistently.
Now, that's great for stateless services, which are easy. But what about the services that actually need to remember things? Managing stateful applications in containers feels like a whole different ballgame.
It is. It introduces the whole complexity of persistence. You have to remember a core design principle of container systems. Containers should be ephemeral.
Disposable.
Exactly. They can be destroyed and replaced at any moment. So you can never, ever store critical long-term data inside a container.
You have to externalize the state.
You have to. While you can use things like Docker volumes to keep data around if a container just restarts on the same machine, for any kind of real production scaling or high availability, the state has to be managed externally.
So you mean using managed databases, cloud storage?
Right. Things like a managed PostgreSQL database or cloud storage like AWS S3. These external services become the long-term, durable memory of your application. That way your data is safe, even as containers are constantly being destroyed and recreated during scaling events.
Okay, before we wrap this journey up, let's touch on 2 quick optimization tips that just make the whole workflow more efficient. How do we make those images as lean and mean as possible?
The most essential technique here is something called multi-stage builds. It's a way to separate the build environment from the final runtime environment.
What does that mean in practice?
Well, think about a compiled language like Go. To build the application, you need the entire Go compiler and the SDK, which could be hundreds of megabytes. But the final compiled binary that you actually run, that might be tiny.
So you use one container stage with all the build tools to compile the code.
Yep.
And then you copy only that final small binary into a second minimal runtime container, something like a tiny Alpine Linux image.
Precisely. The final image size can be, 90% smaller or even more.
And that's faster to deploy and more secure.
Much more secure. You're not shipping your development tools into a production environment.
Makes sense. And the final tip.
It's the simplest one, but people often forget it. Use a Docker ignore file.
Okay.
It's just like a .git ignore file. It tells the Docker build process which files and directories to completely exclude from the build. Things like log folders, local caches, large development files.
So you're not sending a bunch of unnecessary junk to the Docker daemon.
Right. And on a large code base, that can make your build time significantly faster. It's just good hygiene.
That was a pretty comprehensive tour. We've gone all the way from the idea of that single immutable blueprint, the Docker image, to a whole system that's resilient and scaled.
I think the core architectural takeaway here is that Docker really does enforce consistency and portability. It solves that works on my machine problem once and for all.
And then by layering on these infrastructure patterns, Envoy for traffic, Prometheus for insight, circuit breakers for fault tolerance, we end up with systems that can degrade gracefully instead of just collapsing.
That's the goal. Resilient by design.
So for the final provocative thought to leave everyone with, let's consider the natural evolution here. We've designed a really nice system for, say, 10 or 20 microservices. But what happens when your organization grows? What happens when you suddenly have hundreds of services running across multiple data centers or multiple cloud regions?
Right. How do you coordinate the deployment, the networking, the scaling, and the self-healing across that massive distributed fleet of containers? Globally, continuously, and automatically.
That, I think, is the architectural challenge that leads us directly into the world of large-scale container coordination.
And specifically, the really heavy lifting done by sophisticated orchestration platforms.
And that's a deep dive that fundamentally changes how you even think about infrastructure management itself.